ADC converter, 8-bit ADC. Look at the pinout on the left. What do you get out of a chip like this? How do you run this? What do you get out of a chip like this? What comes out of it? Individual bits. This is an 8-bit converter. So what you have falling out on your data out channel, 8 binary lines. What do you do with those? It's great to have a chip which has 8-bit on some pins somewhere. Now what?
You go do whatever you want, store the sound or process it further. It's just a step in the process. You do whatever you want.
Yeah, I understand that. No, I give you that chip in your hands. What do you do?
I wire it up to my speaker and plug it into the computer so I can record things.
You wire it up to the speaker and you put it into your computer.
I attach the 8 out bits.
Yes.
Through some.
To what exactly?
Sorry?
To what exactly?
I could put that 8 bits to a serial converter, plug it to USB, write a driver, and make it a microphone.
Do you think that's a common way to convert videos? Obviously not.
Yes.
Okay, so how do we do this in real life? What do you do with these 8 bits which are falling out of them? Come on, start thinking a little bit. You had computer architecture. You know how computers are actually built, right? You put it into the memory. But what you're actually saying is you want to put this into memory. My question is, how do you get this into memory? And you suggested a version of the only thing which my computer has is a USB port, so you have to have a parallel to serial to USB, and then writing a driver to the whole thing, which obviously is
maybe you connect it to hardware registers, or
you connect it to hardware registers.
Or IO pins or something like that.
IO pins. Okay, guys, have you ever seen a CPU before? Seriously. How is the CPU accessing memory outside?
It's a memory controller inside CPU.
Speak up.
It has a memory controller inside CPU.
It has a memory controller inside a CPU. Okay, and then bus. Bus is a good thing. Okay, and then where does this thing come into play?
Inside the processor.
You can just wire it into the bus, and the bus also feeds into the memory, or you can have your own cache. You cache it to 32 bits or 64 bits.
You cache this. How do you cache this?
You have kind of a small memory on your own. Once you go on your not cache, but like buffer.
Okay. It's just 8 wires here. What do you do with these 8 wires? I mean, your suggestion was the most productive and the only one working so far. But obviously there must be a better way. How are I/O devices on your laptop, which are all using in front of you, almost all of you? How are I/O devices? How is your network? How is your speakers? How is your everything connected to your CPU? Say again?
It's coming to like the source bridge. Where currently there's only a source bridge.
North bridge, south bridge. Yeah. What does that mean? What is that architecture-wise? How does the CPU go through machine instructions to access your I/O devices. How does that? What's the process here?
Control unit.
Second?
Control unit.
Control unit.
So you get the analog, so you convert it to digital, and then go to control unit to see what operation needs to be done.
Goes to control unit. Where's the control unit?
In the CPU.
The control unit in the CPU knows about your I/O devices.
I think it's mapped into memory address.
It's mapped into memory.
Yeah, like the section of the address space for I/O devices.
Yes. Okay, we are getting somewhere. What all CPUs today are doing is that all the I/O devices, because there's a large number of them, are mapped into address space. Right? Somebody has to do that. Can you just take 8 bits and wire them on the bus and say, well, must be somewhere in address space? What's the way to actually access that? What needs to be done to communicate with the bus? Do you have any concept what a CPU bus looks like, how a CPU bus works? Do you have any concept how a bus works in general?
Yeah, well, the CPU wants to access a certain memory. It works out what that memory is, puts it on the bus, something else stores that in whatever RAM location module is saying, I want whatever is accessible at this address.
Okay.
Right? And that can be wired up to your RAM or whatever, or your I/O devices. So you have to physically work out so that when the certain combination of switches or whatever is in the way that it's pointing to a certain address space, the wires go through hooking up to chip instead of whatever else it may have been going to as different, because just at the level of bits and logic,
Sure.
you know, just different paths go everywhere from the straight into your network interface to just normal RAM or whatever.
Okay. Yeah, good. Getting somewhere. Do you begin to see the process? How to go through a bus system? Now, what the CPU is doing is the CPU is putting up a load or going through a load or store instruction. It's the only thing what a CPU can possibly do. In this case, it may go through a load instruction. That means it's put an address on the CPU bus, and this address needs to trigger something. If you have memory wired up on your CPU bus, there's a decoder. There's an address decoder, which responds to certain addresses and then activates memory modules, activates devices, and tells those devices, your time, put something on the bus now. The CPU has put this address out. In order to put data on the bus, somebody has to do that. This is not just taking a soldering iron and putting those 8 bits onto the bus. There has to be a controller in between. Those are device interfaces. Those device interfaces have to be able to communicate with your main CPU bus. This device doesn't have that. There's just 8 bits falling out. Either you take those 8 bits and take that into other parts of electronics of your own and further process that, or you need to put another controller in between this thing and your bus so that the controller can respond to a certain address, can communicate with this thing to get the data out in time, puts it on the bus in the right spot. This is just 8-bit. You probably don't have an 8-bit CPU or an 8-bit bus. At which point on your bus do you put that on? To decide that, etc. So that means we need, in practice, slightly more advanced devices, like, for example, this thing here. Another frequently used one has a few more pins now. And one thing you see is there is one element of it, which is called the fully differential self-calibrating 12-bit AD. That's one module of this whole chip. And there's a lot of other things going on here. Most of them are concerned about how do you communicate with this AD converter. You need to set parameters in this AD converter. You need to tell this AD converter, for example, when, how precise, how fast, how frequent. And you need to get the data out of the AD converter finally accessible to a computer environment, to a computer system. This is, as I said, in most modern computer architectures, done via a memory interface, via the bus system. And what you see down here is a bus interface. This bus interface has a number of wires which you can then use. This is 16-bit. Those, in fact, go directly on your CPU bus. So you can take the soldering iron and wire those 16 bits on your CPU bus. I have a few more. You have 5 address lines which go into that thing. Now that's an interesting observation. 5 address lines. Why? I can look at it from 2 perspectives. Why only 5? Or why 5 at all? Why does it have 5 address lines?
Presumably you need some bits. Maybe there are multiple devices that it's choosing from to do the conversion.
Yep. Okay. What does it tell you what this thing will most likely look like from the perspective of the CPU? Yes? How much memory?
2 to 5.
Exactly. So this will not look like a single memory cell to the CPU, but you can select inside this chip 2 to the power of 5 possibilities. Right? So you have 32 possibilities, memory cells to choose from, which are all mapped onto this device. So if you look at it from your CPU, it looks like 32 words in memory. Okay, what are the rest of the stuff? Next one is interesting. CS. Anybody has any idea what that stands for?
Like child select or control select or something.
Yeah, close. So it's not child support. It's also not computer science.
Like control select.
Chip select.
Chip select.
No, exactly. Chip select. That means this is the one wire which always has to be triggered when any communication with this one happens. And this is also the wire which you use to place your chip into a certain memory area. So one thing which is not on this picture here is an address decoder. You want to have this appearing in a certain area of your memory, which means that whenever a certain combination of addresses appears on the bus, this address decoder says, that's mine. And this address decoder goes directly into the chip select, activates this interface, and this thing can talk to the bus. So only if chip select is active, this thing is allowed to interact on the bus. Right? What it does internally, where it reads from, where it writes from, is controlled by the address lines. And you need a few more lines to communicate on the bus, namely, you have to tell them, is it read access or is it write access? You have to tell this device in which direction it's supposed to drive the bus. Right? And what ALE is, I don't know. I don't remember what that was. It also must be something with the bus interface. Okay. So what are the boxes are interesting on that diagram here? The lineup down here is basically what you will expect to see in these 32 words when you look at it from the CPU side. Some of these words will be a configuration register. Some will be an instruction RAM. So 8 memory cells in sequence which give you this information you want to program this thing with. Interrupt registers, telling this thing what kind of events is supposed to trigger an interrupt. There's also an interrupt output from the interrupt control logic in that chip. This interrupt output is, of course, also to be wired somewhere in your CPU. Usually goes into your interrupt controller. But this device has only one single interrupt output line, nothing else. Okay. You have a sequencer in that thing. Yeah?
I just wondering, there's 16 bits on the data bus counter, but we have 32 memory cells to choose from.
We have how many?
2 combined, 32 memory cells to choose from.
Yes, and you're worried about what? About the FIFO 32 times 16?
Yeah.
Okay, no.
We only have 16 bits to
Yeah. So the FIFO register tells you that you have 32 words in that FIFO area here, but it's called FIFO for a reason. This is not random access area. You can only pull out the latest reading out of this register. So this FIFO block here appears on your memory mapping area only as one memory cell. And it will exactly operate like you expect it now. You read from this FIFO system, from this address, and while reading, you will also delete it from the device, just by reading it. You will read it from the device, it will be eliminated, it will be switched to the next entry in the FIFO, without you doing anything else on the device. That's the first hint where you see that it looks like memory, but it doesn't behave necessarily like you expect memory to behave. You're not used to the fact that reading from memory is side effecting. You expect reading from memory, you can do the same thing 5 times and you read the same value 5 times. That's not true on hardware devices. Not necessarily true, at least. Okay. So, what do you find inside that thing? 8 multiplexed AD converter channels. Okay. What does that mean? What does a multiplexed AD converter could possibly mean?
Read from one of 8 analog signals at a time.
Yeah, read from one out of 8 signals which are wired to that controller from the outside. But it's a multiplex controller environment, which means that you actually physically have only one AD converter. But you can control this AD converter to tell him first convert from this input line, convert from this input line, convert from this input line. You can choose from which of the input lines you want to take information in. How do you choose that? We will see in a second. You can choose the resolution of the thing, you can choose the sampling frequency, power consumption, 15 milliwatts, not particularly low, but also not particularly high. It has a power down mode, like most of these devices have, and it's important to indicate what the power down mode power consumption is. Why do these things have a power down mode? Yes. Almost all of your devices are only used sporadically and are asleep for almost all of their life. So you only power them up when you need them, and you will close them down for all other phases. Now, for devices which are connected to the mains, that's not so much of a problem, but anything which is battery powered, you of course want to be able to make it survive for a long time, so you power it always down.
Would that be a part of like chip select, depending on chip select?
No, it's you have to actively program this device to go into a sleep mode. It doesn't automatically go in sleep mode. The chip select is only for the communication on the memory bus. The chip select itself has nothing to do with the power down mode.
Converting bits, even though it's not expressed.
Yes, yes. That's also very important. This is a completely you can also look at it as an independent CPU if you want. It's not a full-fledged CPU. It does have a sequencer. It does have instructions. It does things on its own. And you can program it to communicate with the main CPU. But yes, it does a lot of things while the CPU is not looking. It actually has to do a lot of things while the CPU is not looking. Think about the previous picture where we see, no, you have it here. 32-bit conversion in FIFO mode. First in, first out buffer inside that chip. Now this only makes sense if you assume that this device works on its own. If you would need to trigger every single conversion actively from the CPU, start converting that one, give me the result, start converting this one, give me the result, I wouldn't need that buffer. Right? But here you operate differently. You tell this device, start converting at this frequency from this input channel or those 5 input channels and dump all the results into this buffer. And let me know when you only have so and so many words left in the buffer. You can tell this device, for example, trigger an interrupt for me when you have done so and so many conversions. That I can start catching up as the CPU, and then the CPU reads it out of the buffer quite quickly. And you can empty this buffer a lot faster than the AD converter can fill it from the other side. It frees up time on the CPU can do other stuff, and you let this run in the background. For example, if your sampling frequency is much lower than the clock rate of your CPU anyway, so you have your sampling frequency at a few hundred kilohertz, and of course that takes a long time from the perspective of the CPU to even do a single conversion. Okay. Self-calibration in diagnostic mode is actually quite common for AD converter, that you need to be able to calibrate these devices. Those are quite sensitive. We talked last time about calibration voltages, reference voltages, which have to be set carefully. And these devices have internal calibration circuitry, which can do this occasionally by itself. And you have to actively trigger that, or you program it. It does it regularly so and so often. You can also program it that it does it regularly after every conversion. And you can physically hook it up to an 8-bit or to a 16-bit bus. What do you do with a 32-bit bus? Let's leave that open for a moment. So, now comes the computer science perspective. Now that we have connected that thing to your actual CPU, the computer scientist starts reading this data sheet. Those are the most interesting parts of the data sheet where you start usually trying to get yourself familiar with what a CPU can do. Don't get discouraged, there's more. So this is only about it. There's only a few of those. How do you read something like this? What do you find on a sheet like that? Okay, welcome to address lines. We see a few of the address lines here now enumerated, which means inside this global memory block, which we allocate for our AD converter device, we have now things happening at different addresses inside this block. And these addresses are just enumerated here. What happens inside of them? Now we assume a 16-bit bus. Hope we have a 16-bit bus to connect to. Then you see what every single bit in these words, which you see in memory, is actually doing or indicating. Instruction RAM is a whole range of addresses. So everything which starts with A4 on 0 is all instruction RAMs. All instructions. Then starting with 1, we have a configuration register. A few funny ones to start with, straight out. If you look at this middle column with the configuration register, the first 4 bits are don't care. What does that mean? just that. You don't care. So whatever is in there or whatever you write to, the device doesn't care. And if you find anything in there, you shouldn't care about the contents either. Commonly, they're actually physically not wired up to anything. You're actually banging into empty air if you try to write anything into these don't care registers. There's nothing wired up on the other end. You're talking to an open phone. Okay. But then there are interesting other ones. Diagnosis flags. This is an interesting one. These diagnosis flags, in some of the devices, the manufacturer tells you, don't touch that. Don't go there. That's for me, not for you. So they use some of these lines for internal quality control and checking of those devices before they hand them out. So they've hooked them up to their configuration computers to run a number of diagnostics on the whole thing. And some of these bits are actually reserved for that. They are not meant to be used in production. Yeah?
If you don't care, is it possible to change those 4 bits while you're reading the rest of the configuration stuff?
Yes. Yes.
Anyway,
Don't care. You can also exploit in the sense of you can write a whole word and you can just leave that as noise in memory. You don't have to set that. You actually don't have to care whether you write anything in there. It doesn't do any damage either. So don't care is like that. Diagnostic is not like that. So if you coincidentally write something into those diagnostic bits, the manufacturer tells you, warranty's off. The guy played with my device, set some of the diagnostic bits. I'm not feeling responsible for what's going on here. The test one, we will talk about these in more details. We have to actually look through the meaning of these bits a little bit more carefully. And that's the rest of it. Some more instruction RAM. So, and each of the that is actually only the instruction RAM. Each of the instructions has the following entries. What does it mean? An instruction for an AD converter. You know what an instruction on a CPU is? A machine instruction. Now, does your AD converters all of a sudden introduce machine instructions? Yes, they do. It's a different programming language, if you want to. You have now more instructions which you can use to actually program your devices here. Now, they're very simple instructions. So don't get disheartened. Very, very simple instructions. The first 2 are indicators to the sequencer which runs in there. You know what a sequencer is in a CPU? Controls which instruction comes next. Right? You also have a sequencer here. You have to determine which instruction comes next in your AD converter. Now, the information for the sequencer here is quite primitive. No, you don't have a conditional jump or something like that. Don't have a conditional branch. But you have a bit which says, this is the last instruction in my sequence of instructions. Please go back to the beginning to instruction number 1. And it starts again. If you don't set this, it takes the next instruction. So there's only the information for the sequencer. Is this the last instruction in my sequence, or is that still something, or is there still something following after that? You can tell it to pause at this point and to wait for a specific event. The next 2 lines, the next two fields are telling from what I/O wires am I taking my input. Now, why do I have 2? I have a V in plus and a V in minus. Why do I have 2?
Is that like exactly where they have, like, there's a signal as well as the gain signal, and they subtract them to take out noise in the transmission?
Yeah, but it has nothing to do with noise, really. But you can use it for that. It's a clever idea. But in the first instance, it's a much more primitive thing. You just have a differential input instead of an input which is with reference to ground. That means you can measure stuff which is not necessarily relative to ground, but it can be relative to each other. And yes, you can just simply program that thing so that the negative input is ground. And you have what you would expect from a level conversion directly. Okay. Synchronization, wait for an external synchronization signal. That's interesting. AD converters often want to convert something which comes from the outside. Right? So whether the signal is currently available is not necessarily clear. So maybe you have, for example, want to convert a video signal, and when this video signal is actually available on my input lines is dependent on the sync signal, which is also some part of my video connector someplace. So I could use this sync signal on the video connector to trigger this AD converter to actually read the value in to convert it. You can tell your AD converter to prepare yourself for a 12-bit conversion between these two input lines and wait for the trigger from the outside. The trigger comes from the outside, do your conversion, store it someplace. And you can explicitly program a timer so that you say, from now on, wait so and so many cycles and then convert. Okay. What other instructions do we have in there? Then we have to select the conversion resolution. We have to set whether this is an 8-bit or a 12-bit conversion. Watchdog activates comparisons with two programmed limits. What could that mean? You can set your AD converter into watchdog mode. What does that?
Isn't it if you don't get it output by a certain time, you reset? Or you enable to set an interrupt thing. It's not fast enough, I think.
What is not fast enough?
Like the output time, so you take too long to convert that bit.
Good idea, but
reset the time.
yeah, good idea, but no, that's not what that means.
In this case, it looks like you're actually checking the values between two limits to that balance.
Yes. So your concept was watchdog in time. And most computer scientists have the concept that watchdogs have a relation to time, often have. That you set a watchdog timer. This is not a watchdog timer. This is a watchdog value limiter. And often, if you want to monitor, for example, a certain temperature, it's nice to actually measure this temperature and to plot something on your little device, how the temperature progresses at the moment. But often you actually don't care about the value of the temperature. The only thing you actually care about is if this temperature goes outside my limits, please press the big alarm button. It's the only thing you're interested in. And for that, you can use the watchdog limits here. You program, as you also see, you have two limits here, where you can say that this is above or below one of these limits, then trigger watchdog interrupt and alert my CPU something is wrong. In fact, if you program this thing in watchdog mode, it doesn't even store the result. It only gives you the watchdog interrupt, and then the CPU can trigger an actual conversion into reading the value in. That's the idea behind it. Saves tons and tons of CPU time. You don't ever read information you don't care about in the first place. You leave this completely offline to this device. Cool. So what else do we have? Acquisition time. It's a bit more for the electrical engineers. The electrical engineers will have a bit more idea what that means, because the acquisition time which you have also relates to the impedance which this device will show to the outside world. Don't worry too much about this at the moment. And the two limits are just values which this is compared against. So, okay, back to your programming. How do you interact with that thing now in your programming language? You have this beautiful data sheet. Let's have a look at this whole data sheet again. And you begin to understand what this device can do. Great. You're getting motivated to actually use it. And then you have this blinking cursor in front of you. And I tell you that I wired up this device to address so-and-so in your memory. Over to you. Now what?
You start by modeling the configuration parameters.
Yes. How do you do that? How would you do?
Specify how they represent in memory, like what size they are,
Yeah.
how they get written into memory, like where to, where you're from.
Okay. So if I want to, for example, change or set a specific instruction which tells me I want to have an 8-bit conversion right now, and I want to have this regularly happening continuously from now on out. What do you do? How does that look like in programming?
Your instruction is a record and has fields with different parts, so like one can sync, one can make a timer.
Yeah, exactly. Okay. But this is producing a record out of this one is of course a pretty touchy operation because every bit counts here. And this is not up to your compiler, if you define a record of some sort, where to put the stuff of the record, but you know where the stuff has to be in memory. Bit precise. And it's not too obvious to express this in your programming language, is it? Can you express this in your programming language? Okay. Can you express this into your second favorite programming language? All right. Good. So this is what you could do. Now we have to define an instruction here. And the first thing you do, you translate these bit patterns into enumeration entities. Interestingly, the channel for plus, the type for the plus channel and for the minus channel are actually different, because for the minus channel you have the option in this device, one of the values which you can set here means ground. For the other one it doesn't mean that. For the other one it means channel 0. So they're already not the same, so you define two different enumeration types for that one. And the first four you can do pretty much in every programming language. But what you need to do now for the enumeration values which you have there, the first thing you need to do is you need to assign exact values which are supposed to be represented by that. That's not necessarily the natural order, because often you have actually gaps in there. So if you say that I have an enumeration type from 0 to something, that is often wrong. Because if you read these data sheets, you have often gaps in there. 0 means that, 1 1 means that, 1 1 0 means that, and the things in between don't mean anything. So a linear enumeration type is not cutting it. You need to explicitly set these values to exactly the bit patterns which you want to trigger with that. This is what we do here. We say that the values for channel is supposed to be that. The values for the resolution, 0 means 12-bit, 1 means 8-bit. And then I can define a record out of all of these elements. But now you're coming back with, well, the record is nice. But how do I tell my programming language where to align the elements in that record so it actually fits my hardware device? So that's the next thing we need to do. Can express this, for example, like that. We have defined a record which is called instruction, but now we're also saying for instruction, use the record alignment like that. You tell your compiler explicitly at which bits and bit areas this has to be allocated. Easy enough? Make sense? That was an awkward moment to switch off the project, huh? Please. I need that. No, I broke it. No. He's willing to come back. Okay, here we go. So there are a number of other things. You will actually see that the syntax which you will be using will be a little bit different, but that's the basic idea. You have to tell the overall size of that record as well, number of bits which is supposed to be, the instruction alignment. This doesn't go naturally. You have to actually tell it that this has to be aligned to a certain border. And many of the devices will in fact produce a bus error, will crash your system if you address them in the wrong alignment. If you read your data sheets later on, it will explicitly say this register has to be addressed in full word size. This has to be addressed in half word size. This has to be addressed by a byte load instruction. This has to be explicitly told to the compiler or whatever you use for that one. You control the bit order inside my words, how the thing is supposed to be enumerated. Then you can define an array of these instructions, here from 0 to 7 to refer exactly to the instruction numbers as they are appearing in the device itself. And that's a bit clunky. I wouldn't use a pragma today anymore. You can use attributes for that, but you can also use a pragma for that to tell it that if you allocate this array, no gaps. It has to be completely compressed. Also doesn't go without saying, because if you do this on a 32-bit machines, you would have, by default, gaps between your array entries. Right? So you have to pack it down. Then finally, after all of this type, because so far we haven't actually instantiated anything, we define a variable, ADC instructions. Cool. And now comes the grounding. We say this variable is not supposed to be allocated somewhere by your compiler. This variable is supposed to be happening exactly at this address. This will be nailed hard to this address in your memory. Hopefully this was the address where your device has been wired to. And of course, this is something you cannot know. You just have, or you hopefully know somehow. You cannot test this. You cannot verify that this is the right one. This coincidentally was your speaker output, and you will probably find out that this playing on those registers will have different effects. Okay. So what do I do now? I use this variable, this array, which I just defined, and set two instructions into this variable. First one tells me that I want to have a conversion between channel 0 and ground, so the absolute value of channel 0, with a precision of 8-bit external synchronization. I want to wait until I have an external sync signal before I do that. And I have a certain acquisition time available for that, followed by the second instruction, which is also the last instruction which I want to give to this conversion system, which takes the value between channel 1 and channel 2, the differential voltage between these, converts them as a 12-bit, and there is no timer, delay, watchdog, or external synchronization involved.
Do we have this ADC on boards that we use?
Now I show you the interface to the actual ADC which you have here. This is kindergarten. This is the small-scale version. The ADCs which you have on your devices are way, way more complicated. But you have to get the idea first, how that looks like. Yeah.
After the last instruction, does it go back to 0? Or
Yes. Yes. This is end of loop, and this is a very, very simple sequencer. The sequencer can only do two things. It can go to the next instruction, or it can loop back to instruction 0. This is calling it a sequencer is a bit of a euphemism, but this is what this thing is doing. So, what is happening now? After you have done this?
Just run it directly into the device by the memory bus and the like that.
Okay. When do you write this into the memory bus? When do you write this into the device? When does this happen? Say again? In the ROM?
Get the files like, I guess, small pieces of ROM and
No, hang on. You wrote this program. You define these types. You compile this. You run this. Does anything happen?
You need to synchronize with the actual memory.
You need to synchronize with the actual memory. Flash it into the memory. Any different opinions?
It might be a bit set to actually enable or start it. This ADC.
Okay, so there may be other registers, so there may be a configuration register. So assume that I also have done this for a configuration register which actually enables the device in principle. Okay. No, you're all a bit pessimistic.
What specifically did that thing previous slide put in a memory address to?
Okay, now you're actually on the right track. The specific thing you had on the previous slide, this thing here, for instruction address, use this address.
So is that already mapped by
Yes.
by the control into the hub?
Your compiler takes that seriously. Your compiler just allocates this variable, which you use in your higher programming language, hard to this device. So whatever you play with this variable on your higher level programming language is directly playing with the device. There is nothing to be flushed, to be synchronized, or anything else in between. You play with this variable in your high level programming language. Things happen instantaneously. There's nothing in between. Nothing to power up, enable, copy over, nothing of that sort. You work on the actual device, right here. Yeah?
Then I think it would be better to write this into the memory and then enable that one. Because sometimes if you assign kind of part of the instructions and
Yeah.
the device just goes.
Yeah, that's a good thought. So if you have an awareness that all the registers which you are now setting by using your variables will be directly accessed on hardware, each individual writing a few bits, writing a word out on hardware will have direct effects. Some of these effects will, for example, require that you wait for a few microseconds. Because if you power something up, an actual hardware device, it may not be ready after one CPU cycle. So you have to often be aware, those people who have been actually using the controller in 2300 have some idea about this. So you enable an interrupt. That doesn't mean it's instantaneously there after the next clock cycle. You may need to be a little patient and wait for 2 more clock cycles on your main CPU before your device caught up with the real world, before your device is powering up, before your device is ready for the next instruction. Yeah.
This is directly mapped to the hardware. How do you get around the atomic freeze write problem? If it's mapped directly, if on the CPU side, if you're trying to read a value and it's going through, but another device has direct access to that memory, that can start messing with the bits, even if it's reading through it. How do you make sure that's not?
this is why usually you don't give device addresses to users. Huh? Because you have to make sure by the whole design of your operating system, of your library, of your interfaces, that this cannot happen, and you are right in, you cannot actually prevent that. If I would give this address to 5 tasks in my ADA programming environment, and all of these tasks are hammering my AO controllers unsynchronized, that's probably a really bad idea. And your device would probably go completely haywire from the non-atomic access to all the different registers which you have in there. So you have to make sure, usually, this is what usually is called then a device driver. A device driver is very rarely, at least on this level, concurrent. Device drivers will need to control these registers sequentially for that reason.
But even if the main CPU has this AO code running, and it's the only one accessing that memory address, then the actual AD chip itself can also write to these memory addresses. And even if you lock all your ADA side down, you still have them interact.
Yes.
So how do you tell them to not mess with what you're reading or that sort of thing? Make sure you don't get messed up with what they're doing.
Yes, we come back to that. Because we have to now also acknowledge that some of these are read-write, some of them are only read, some of them are only write. You cannot physically read from them. If you try to read from them from your higher level programming language, your system can crash. It's all very encouraging, right? So yes, by messing with hardware, you always have a physical effect to the world around you, which means you can burn stuff down by actually doing the wrong stuff in your programming language. Right? Now you distracted me. Read-write, exactly. What happens if my device can actually write to that? And how do you handle this from a higher level programming language? One thing which you will see in the interfaces which you will be using is that those registers which can be written from the device from the outside are marked as volatile in your compiler environment. What does that mean?
It disables some kind of optimizations, doesn't it?
Yes.
There are kind of some kind of assumptions with normal memory with the values that are going to be read and write in a certain way.
Yeah.
It doesn't necessarily hold the amount of volatile.
Exactly. So usually, you as computer science people, you assume you write something to memory, and I'm the only process who has access to this variable. This is my local variable. This cannot change until I touch it again, right? But a volatile variable is of a different character. A volatile variable means that you always have to consider the possibility this can change without you looking. This can change in the background just by the device using this variable without you having any interference with that one. And of course, all of our compilers use a lot of optimization in the sense exactly how you said. If you know that this is a constant, this is not being changed between these two sets of instructions here, I can optimize that very differently. I can take this, for example, into a register, and I know that the value could not have changed, so I leave it in the register for a little while until I can use it again in 5 instructions in that register. If this is a volatile memory address, I have to, for example, as a compiler, always reload this. Every time your high-level programming is reading from that one, you cannot assume that the last read is still the same. You always have to reload it from memory bus. Make sense? Cool. Right. So, doing the same thing in C. You defining enumerations, structs, setting some values there. Also see a little drawback which you You cannot have compound assignments in C, that you set all the values of a record in one go. You have to do this step by step, which means you can easily forget one, which can also mean that you're not telling the compiler that this is a single assignment. If you compare this with here, you actually set the whole record with a single instruction, which A, enables the compiler to optimize more, do it in one instruction. B, reminds you that you haven't forgotten to set any of the record entries, because if you leave any of the record entries out here, the compiler tells you off what's the value of that. And for a hardware interface, that's a good reminder that you get reminded of that. Okay, other than that, does it all look okay from the C perspective? Yeah, it looks okay, but it's plain rubbish. Don't do that. None of this is in any way portable. You have no guarantee unless you have a specific C compiler which is optimized for one specific microcontroller and does the alignment according to what you need, what you expect it to do. This is the definition of non-portable. C does not define record alignment, struct alignment, bit ordering in any way. And there's also no attributes, no pragmas to control that. So you can't do that. What do you do in C? What's the C way of programming these controllers? Use the what?
Use the direct adjustment.
Yes, but how do you formulate, for example, an instruction? How do you get the bits set? You bash the bits out. Okay, can you express this in C? Bashing bits out? What does it look like? You have a constant, and you mask it, and you shift it, and now we all shuffle one to the side, and then we set another one, we shuffle all to the right, right? This is exactly right. This is exactly how you do this in C. You get yourself, for example, write yourself a function like this, which sets a certain bit at a certain position, and this is how you just do that. Masking, shifting, getting to the right spot. How does your Ada compiler do that? Well, your Ada compiler does exactly that. But the point is, you don't have to program that. Because and you get all of these bits in that kind of interface to the right spot. You may be lucky. I always need 3 attempts before I get it right. So I'm not sure whether this is... well, and there's, of course, absolutely no abstraction to save you from setting wrong values in undefined areas of any sort. There's no compiler feedback at all. Another side effect which you see here is that in those definitions, actually I'm showing you this later on in an interface which refers to your compiler instead. I think that's more interesting. So, to get the full story, this is the configuration register. And now you can just read this data sheet and just directly translate this almost mechanically into data structures. Once you have this translated to data structures, you are type safe. You cannot set the wrong thing accidentally just by using some numbers wrongly. What do you have? Start the sequencer, reset the whole thing, auto-zeroing everything. That's the short calibration. You have a full calibration, which takes almost 5,000 clock cycles of that thing. And this takes so long that it automatically produces an interrupt by the end of this auto-calibration phase. You can set it into standby, powering it down. What else do we have? You can set an auto-zero in the configuration register, which means that you have an automatic calibration before every conversion if you want to be a bit more precise. If you want to convert 12 bits, you better be a little bit careful that your AD converter is nicely calibrated. You define what synchronization mode is used on the I/O pins. You define which is my current instruction. This is your PC, your program counter, which you can explicitly set. Then this test bit. No, it's actually the other way around. The test bit is the one which is actually forbidden. The diagnosis bit is the one which you are supposed to use. Got this the wrong way around. So don't touch test. Diagnosis is fine. Okay. This is the pseudocode version of the sequencer. This is the sequence of operation inside of your device. Has a white loop around it. You reset it to 0 in the beginning. See whether it's an auto 0 bit set or full calibration set. Then you do a calibration before you do anything else. If this specific instruction at hand has the timer bit set, run a timer first. Then you do the actual conversion. You trigger the actual AD converter to give me a value. And then you see two cases. Is this a watchdog operation? Then the only thing I'm doing is I'm comparing it against the watchdog limits. And I'm done. Operation is complete. And otherwise, I'm potentially waiting for an external synchronization signal, and then I store it into my buffer, which is accessible from the outside. And then the actual sequencer part of it, either I reset it to 0 or I take the next instruction after that. The FIFO register is read-only. Surprise, you cannot write into it. But it also means that every read operation, as we said before, into that register will give me the oldest value in my buffer and immediately deletes it. So not only write operations on hardware have side effects, read operations have side effects too. You can set this at a certain fill level to give you an interrupt, so you're not accidentally overrunning. And this interrupt can then, for example, trigger a DMA transfer. Why would you do that?
So you can be busy with all this stuff while the data is on.
Yeah. You will in fact do this later. You trigger a specific event on I/O line or on I/O interface. You then also trigger a DMA transfer so that the data is automatically stored somewhere else in memory where you can, in all calmness, access it later on. You can, for example, unroll this built-in FIFO buffer, which you can only access the oldest value from. You can just tell a DMA controller, read from this thing 16 times, and roll it over in this memory block and write these words which you read from there in there, and then leave me alone. I can look at the CPU later on in this area, what are my 16 latest values, and can do something else. So often these interrupt lines are not necessarily handled by your CPU, but only by DMA controllers, direct memory access controllers. Those are independent units which are only there to shuffle memory between devices and memory or between memory areas. Obviously, this thing can trigger a number of interrupts, and this is the interrupt status register, which you can use for that. Or you could use explicit polling if you have plenty of time at your hands, or you want to be extremely close to the actual conversion. Polling is not a slow operation, but it's a very CPU-intensive operation. Polling means that you're not going through the whole cycle of triggering interrupt, getting a context switch, saving all the registers, blah, blah. Polling means that you're staring at a single memory cell. Is this conversion done with the full speed of your CPU? And the moment this thing is done, you will get it with the next CPU cycle. Now, you cannot get any more responsive than that. This is more responsive than going through an interrupt. Counterintuitively to what most people think, but this is faster than going through an interrupt. It's, of course, tremendously power intensive and CPU intensive, and it looks idiotic from a program perspective because this CPU doesn't do anything else anymore. It just stares on this one memory cell. Right? But if your life depends on getting this thing the earliest possible, you can do it like that. Right? So, any further questions about such a simple device at this time? Yeah?
So it's got the multiple registers inside it addressed by those 5 bits there.
Yes.
Like, how does Ada know what to do with those bits when it's addressing the device?
You nailed this to a certain address in memory. What you usually do is you define all of your registers for this device, and then you define one large block which has one large record, which has all these registers in one record, exactly in the sequence as they appear in your device. And then the only thing you do on the higher level programming language is you nail the base address of your device to the beginning of this large record, which contains all registers of my device. Otherwise, you would need to set every individual record to a new memory cell here by hand, which is cumbersome. Because in almost all of these devices, they're, of course, in sequence somehow. And if they're not in sequence, you can still program a gap into your register set. Right. Any other questions about that?
What's A0 used for? It's in the data sheet so far.
Yes, this is because what I have been showing you here is the 16-bit version interface of this whole thing. You can also run this thing in 8-bit mode. And in 8-bit mode, A0 is being used. So this is just in 16-bit mode, you always write in 16-bit, so A0 is ignored. So far, so cool? Makes sense? You want to see some more real-world controllers? Okay. I just bluntly copied randomly one of the control registers which you have on your actual device on the screen here. This is the control register 2 of one of your AD converters which you have in your actual machine. And this is the breakdown you have here. Enable DMA, enable the actual controller, continuous conversion, also comment how many of them are read-write or which of them are read-write. In this case, it's a configuration register where everything is actually read-write. Nice. And you see that in the type definitions, those are not just Boolean or, I don't know, range from 0 to 5, but they're all types. Almost all of them are enumeration types. These enumeration types have a specific meaning and they're type checked against those entries. So whenever you set, for example, the continuous conversion status of your device, you can only use the values which are defined in your enumeration type for that. You can only use continuous or single as defined here. You cannot use red or green or any other enumeration type. You cannot use 0 and 1. If you try that, the compiler will tell you this type doesn't match. You can only use that type for that purpose. This sounds so trivial and is of tremendous importance in real world, because if you only have the type integer available for those interfaces and everything is an integer, then you have a tremendous list of constants. So continuous means 27, single means 28. You have a tremendous list of constants. And of course, as good citizens, use the right constants for the right purpose, right? But if you're not, the compiler doesn't have a chance. So use the wrong constants for all the wrong purposes in the wrong registers. And this is all just numbers. This is all just integers. Right? Well, here it is not. You also see that the record has now a size associated with that one. Here I simply use the information that we know how large a word is on my controller. So I say that this is a record which spans a whole word on my controller, and I also indicate to the compiler this is a volatile memory address. Do not assume, do not do any compiler optimizations which assume that you can read this once and leave this in the register for further optimizations. You have to go back every time you want to read information from this thing to actual memory, meaning to the actual device. So first you define it, then you allocate it, you just nail it all down, and there's a surprising amount of redundancy in there. So if you get any of them wrong, can you mess this up so that you get it past the compiler? What happens if you get any of these constants here wrong? Any of these bit alignments wrong?
Maybe it's the wrong size. You specify the size.
Yeah, there are lots of cross-checks here. One cross-check is the whole thing has to be continuous. So the compiler will tell you off, you forgot a bit here in the middle. What's that supposed to be? The next cross-check is every of these data types have to be physically fitting into that one. Every of these data types have a size themselves. They have a precisely defined size nailed down. So this size has to match. The compiler will tell you that you said this is for 3 bits, but the type you have there is actually a 2-bit wide type. That doesn't fit in there. Even if you get that right, you still have the check at the end that the whole record has to have exactly 32 bits. Has to be filling exactly a word. So if you mess up one of that one, you will again be told off by the compiler this doesn't go together. In practice, it is actually really hard to mess that up. You will almost always get a feedback. And I've done this for literally hundreds, probably thousands of interfaces like that. I don't think I had bit alignment mistakes more than a handful ever in my life doing that, because you get told off every time you slip by a single bit. Again, you go back to the world of integer. Yoo-hoo! No compiler checks whatsoever. Okay. Usually for comfort, you define on high level also what my initial state, the reset state of this register is. Can come in handy on your high level programming environment that you know what to expect to be in this register. If you want to start from the reset value and then manipulate it, you can just copy that in here. Because this is high level programming, you can take local copies. You can take a copy of my control registers. Nobody stops you from that. As a matter of fact, you will need to take copies of your control registers quite often. Why is that?
Well, I usually want to read it and change something and write back.
So what do you do if you want to change 5 things at the same time? What do you do if you say you want to change 2 things at the same time? You can, of course, just use the actual hardware mapped variable and write to this record entry, write to this record entry, write to this record entry. But that means that every time you touch that, your compiler will write this out immediately. That may have been atomicity, that may bring atomicity problems with it. If you take a local copy of it, manipulate all the elements which you want to change in your local copy, and then write back the whole register in one assignment, then you write the whole word in one go, and you don't have these atomicity issues which you may have had otherwise. Right. Okay. I think this is as far as I would want to drive you today. Yeah.
Is there a nice way to do that when you read it and change units right back? Do you have to write a separate procedure for every pairing of values that you might want to change and write back in one go?
What would be a nice way?
I was just asking.
Okay, so you say it sounds clunky that I have to take a local variable copy, and then I have to change it there, and I have to write it back.
Do you have to
Yeah.
do that in your code every single time that you want to modify it?
Okay. Now, this is driver level 0 here. This is the driver level which directly hacks into the registers of my device level. Now, what you provide on the next level up is usually some function-oriented, procedure-oriented interface, which you give to the next level, which gives you, for example, an interface which says, give me a single 8-bit converted value between these two channels. And I have these three parameters in my function. And this has to be translated down into a bunch of different operations on my registers. And then I return some value there. You're usually providing a more function-oriented interface on the next level above the actual registers. And only in that level, you will need to play with that effect of taking local copies. So you don't have to do this in your actual user code later on. You have a number of abstractions in between before you get to that point. And this local copy taking is always done on the lowest abstraction level. This is only done on the level where you actually touch the hardware device registers. But I don't have any more comfortable way to express this. I don't know that there is any attribute which says always take automatically a local copy and only delay the write back until this happens or something like that. Don't have that. All right. So far, so cool. Did you learn something about how to connect to devices and what it means to interact from a CPU to an actual controller? Did you get some more insights on that? Okay, excellent. I have to call it a day. Next Monday, or no, next Tuesday, we will talk about the whole microcontroller as a whole device. Thanks, guys.